Before we go any further, I want you to picture something very simple. Imagine holding two ordinary bar magnets in your hands. You slowly push the north pole of one magnet toward the north pole of the other. Before they even touch, you feel something strange. Your hands feel resistance, almost like there is a cushion between them. It feels soft, springy, like invisible pressure pushing back. In this video, we are going to explore what is really happening in that invisible space and why it takes us deep into the rules of the universe. Before we begin, make sure to subscribe and click the bell icon so you don't miss our exploration into the hidden logic of science. You know, people come up to me all the time with exactly this question. Students, journalists, and curious people who love science. They feel that strange resistance and look at me with genuine curiosity. I love that look. Curiosity is one of the most valuable things you can have. And they ask a very direct question. Professor Feynman, what is happening between these two pieces of metal? Why do they push each other away? What they usually expect is a simple explanation, something comfortable, something familiar. They want me to say it works like a rubber band stretching or like pressure in water pushing things apart. But here is the honest truth. I cannot explain how magnets work in the way people expect. The reason is not that we don't understand magnetism. We understand it extremely well. The mathematics is beautiful and precise. The problem is something else entirely. It comes from the nature of the question, why, and from the limits of our everyday language. So to answer the question honestly, we have to step back for a moment. In fact, we have to step way back. Because in physics, the question why is a very dangerous one. Let me give you an example. Suppose someone asks a simple question. Why did Aunt Minnie slip on the ice? I might say, she slipped because the ice was slippery. But think about what actually happened there. All we did was replace the word slip with the word slippery. We did not really go deeper. But why is the ice slippery? Well, the pressure of your weight can melt a very thin layer on the surface, producing a tiny film of water. And water reduces friction. Why? Because water molecules can move past one another more easily than the molecules in solid ice. The explanation begins to move from everyday experiences into microscopic physics. This is where the real answer hides. And the questioning continues. Why do molecules behave that way? Now we must talk about atoms. We must talk about forces between atoms. Soon we are discussing quantum mechanics, the laws governing how particles interact at extremely small scales. Do you see what is happening? Each time we ask why, we move one layer deeper. It is like peeling the layers of an onion. At first the explanation feels familiar, but as we go deeper, the ideas become stranger and less connected to everyday experience. Eventually we reach a point where explanations based on common sense stop working. For example, suppose I tried to explain magnetism by comparing it to rubber bands. That might sound helpful at first. But rubber bands themselves are made of atoms, and the forces holding those atoms together are electromagnetic forces. So using a rubber band to explain magnetism is like trying to explain the foundation of a building using the wallpaper on the walls. If we want to understand magnets honestly, we have to accept that the explanation will take us into unfamiliar territory. We must allow ourselves to step into a world where everyday intuition does not work very well. Now let's return to the simple sensation you feel when you push two magnets together. When you press them toward each other, you feel a force. Your muscles feel it clearly. It pushes back against your hands. In everyday life, we associate force with contact. When you push a chair, you touch it. When you lift a glass, your hand grips it. Our brains evolved in a world where forces usually come from physical contact between objects. Because of that, our intuition tells us that if something pushes on something else, they must be touching. But magnets challenge that intuition. When two magnets repel each other, they are not touching at all. There is empty space between them, yet the force is still there. At first, this feels mysterious. It feels almost like magic. It feels like something is happening across empty space without any connection. But here is a question that might surprise you. When you sit on a chair right now, are you actually touching the chair? It certainly feels like you are. You feel the pressure of the seat beneath you. But if we looked at the contact between your body and the chair with an incredibly powerful microscope, we would see something unexpected. We would see fibers from your clothing and fibers from the chair. Looking closer, we would see molecules. Looking even closer, we would see atoms, and those atoms are mostly empty space. If we continue zooming in closer and closer, the picture becomes even stranger. At the center of every atom, there is a tiny nucleus. Around that nucleus move electrons. If the nucleus were the size of a marble sitting in the center of a football stadium, the electrons would be like tiny insects buzzing around near the upper seats. The rest of the stadium would be empty space. This means that atoms are not solid objects in the way we normally imagine. They are mostly empty space with tiny charged particles moving within them. And when two objects appear to touch, their atoms never actually collide like billiard balls. Instead, what happens is that the electrons in the atoms of one object begin to repel the electrons in the atoms of the other object. These electrons carry electric charge, and charges push against each other through electromagnetic forces. As the atoms get very close, these forces grow extremely strong and prevent the atoms from moving any closer together. When you sit on a chair, you are not actually touching it, at least not in the way you think. Instead, the electrons in your body are repelling the electrons in the chair. This invisible electromagnetic force is what truly holds you up. It is the same fundamental force found in magnets, but while we feel it as solid in a chair, magnets let that force extend further into space. That is why your hands can feel the push of a magnet even when there is air between them. The distance is just greater. In the microscopic world, nothing truly touches anything else. All interactions are mediated by invisible fields and forces. Once we accept this, we can begin to understand magnetism properly and the very foundation of the world around us. So every electron in the universe is essentially a microscopic magnet. That means the atoms in your body contain tiny magnets. The atoms in the chair contain tiny magnets. The air around you contains tiny magnets. At this point, you might ask a very reasonable question. If everything is made of these little magnets, why doesn't everything behave like a magnet? Why aren't you sticking to the refrigerator right now? Why doesn't your book leap off the table and attach itself to the ceiling? The answer is that in most materials, the tiny magnetic arrows of the electrons point in many different directions. Some point up, some point down, some left, some right. Because they are oriented randomly, their magnetic effects cancel each other out. The result is that the material as a whole has no noticeable magnetism. But certain materials behave differently, and that difference is where magnets truly begin. Certain materials, however, behave in a very special way. The most famous example is iron, although nickel and cobalt behave similarly. These materials possess an unusual property that allows many of their electrons to cooperate with one another instead of behaving randomly. Because of complex quantum mechanical interactions inside the atoms, the magnetic directions of the electrons tend to line up with each other. But this does not happen across the entire piece of metal all at once. Instead, the alignment happens in small regions inside the material. Physicists call these regions magnetic domains. You can imagine each domain as a tiny neighborhood where billions of electrons have agreed to point their magnetic arrows in the same direction. Inside one domain, the electrons may all point north. In the neighboring domain, they may all point south. In another, they may point sideways. Because these domains are oriented differently, the overall magnetism of the material cancels out. That is why an ordinary iron nail usually does not behave like a magnet. However, something interesting happens when you place that iron in a strong magnetic field. The external field begins to influence the domains. The tiny neighborhoods start to rotate and shift. Domains pointing in the wrong direction shrink, while those aligned with the field grow larger. Gradually, more and more of the electrons line up in the same direction. Eventually, billions upon billions of electrons point the same way. Their tiny magnetic effects add together, and the result becomes strong enough to reach out into the space around the metal. At that moment, the iron becomes a magnet. It is like a crowd of people in a stadium. If everyone is shouting different things at the same time, the noise blends into a meaningless roar. But if suddenly the entire crowd begins chanting the same word in perfect rhythm, the sound becomes powerful and unmistakable. A magnet works the same way. When the microscopic magnetic arrows all point together, the combined effect becomes large enough for us to feel. Now we must talk about something that often confuses people, the idea of a field. When physicists describe magnetism, they often say that a magnet creates a magnetic field around it. This word field can sound mysterious, almost like something from science fiction. People imagine it as an invisible substance filling the air. But the concept is actually simpler and more abstract than that. A field is simply a way of describing what would happen if something were placed at a certain point in space. For example, imagine mapping the temperature inside a room. At each point, you could record a number that represents how warm that location is. The collection of all those numbers forms a temperature field. The field itself is not a substance. It is a description of how conditions vary from place to place. A magnetic field works in a similar way. It describes how a magnetic object would experience a force at different positions around the magnet. However, there is a useful way to visualize this idea. You can imagine the space around the magnet as being under tension, almost as if the space itself were slightly stretched or stressed. When another magnet enters that region, it interacts with this tension, almost as if the space itself was slightly stretched or stressed. When another magnet enters that region, it interacts with this tension. If you bring the north pole of one magnet close to the north pole of another, the field lines between them become compressed. That compression stores energy in the space between the magnets. Nature tends to minimize energy whenever possible, so the system pushes back. The magnets repel each other, trying to move apart and release that stored energy. In this sense, when you push two magnets together, you are actually putting energy into the field between them. When they push apart again, that energy is released. But even after explaining all this, we still have not answered the deepest question. We have described what happens when magnets interact. We have talked about electrons, domains, and fields. Yet the most fundamental question remains: why do electrons behave this way in the first place? Why do electric charges repel each other? Why does a moving charge create a magnetic field? To answer that question, we must go deeper into the laws of physics, and at this level something remarkable appears. Magnetism, it turns out, is not truly a separate force at all. It is actually a consequence of electricity combined with motion and the geometry of space and time. It is actually a consequence of electricity combined with motion and the geometry of space and time. To understand this idea, we have to look at the insights of Albert Einstein and his theory of relativity. This is the part that surprises many people the most. Magnetism is, in a sense, electricity seen from a different point of view. It is what happens when electric forces are observed in a situation where charges are moving relative to one another. It is what happens when electric forces are observed in a situation where charges are moving relative to one another. At first that may sound strange, but once you see how it works, the connection becomes clear. Imagine a simple copper wire carrying an electric current. Inside the wire, negatively charged electrons move through a background of positive charges belonging to the atoms of the metal. Now imagine that a small charged particle is moving alongside that wire at the same speed as the electrons. From the particle's perspective, the electrons in the wire appear stationary because they are moving together, but the positive charges in the wire appear to be moving backward. And here is where relativity enters the picture. When objects move at high speed, special relativity tells us that distances along the direction of motion appear slightly contracted. That means the spacing between the moving positive charges appears smaller from the perspective of the moving particle. As a result, the density of positive charge seems slightly higher. To the moving particle, the wire suddenly appears to have an imbalance of charge, and that imbalance produces an electric force. From our perspective, we call that force magnetism. So magnetism is not an entirely separate phenomenon. It is electricity, combined with the effects of motion and relativity. In other words, when you hold two magnets in your hands and feel them push against each other, you are experiencing a consequence of the deep structure of space-time itself. And that realization changes the way we think about something as simple as a pair of magnets. When you hold two magnets in your hands and feel them pushing against each other, what you are really experiencing is the consequence of moving electric charges interacting through the structure of space and time. That might sound surprising at first, but it is one of the most beautiful insights modern physics has given us. To understand it more clearly, imagine again the electrons inside a piece of metal. Those electrons are constantly moving. Some move around the atomic nucleus, and others drift slowly through the material when an electric current flows. Whenever electric charges move, they create magnetic effects. What we call magnetism is simply the electric force observed from a situation where charges are in motion relative to each other. This connection between electricity and magnetism was one of the great discoveries of 19th century physics. Before that time, people believed the two phenomena were completely separate. Electricity was associated with sparks, lightning, and batteries. Magnetism was associated with lodestones and compass needles. They seemed unrelated. The moment that changed this view came in 1820, when the Danish physicist Hans Christian Ørsted performed a very simple experiment. He had a wire connected to a battery, and nearby he placed a compass. When the electric current began to flow through the wire, the compass needle moved. This was shocking because the compass was responding to the electric current. The moving electricity in the wire created a magnetic influence around it. Electricity and magnetism were suddenly revealed to be connected. What made the discovery even more surprising was the direction of the force. The compass needle did not point toward the wire or away from it. Instead, it turned so that it circled around the wire. That meant the magnetic effect produced by the moving charges formed a circular pattern around the current. This discovery showed that magnetism is created by moving electric charges. A permanent magnet, like the one you hold in your hand, contains enormous numbers of electrons whose tiny motions combine to create a stable magnetic field. But the story did not stop there. A few decades later, the Scottish physicist James Clerk Maxwell looked at all the known laws of electricity and magnetism and realized they could be expressed in a small set of equations. These equations described how electric fields and magnetic fields influence each other and how they change in time. Maxwell noticed something remarkable hidden in the mathematics. According to the equations, a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. These two effects can sustain each other, producing a self-propagating wave traveling through space. When Maxwell calculated the speed of this wave, he obtained a number very close to 300,000 kilometers per second. That number was already known to scientists. It was the speed of light. Maxwell realized that light itself is an electromagnetic wave. What we experience as visible light is simply a vibration of electric and magnetic fields traveling through space. This means that the magnet you hold in your hand and the light entering your eyes are expressions of the same fundamental phenomenon. Once this idea is understood, the world begins to look different. The chemical bonds holding atoms together are electromagnetic. The forces that allow molecules to form are electromagnetic. Even the processes inside living cells rely on electromagnetic interactions. In a very real sense, most of the everyday world around us is governed by the electromagnetic force. Yet even with this understanding, magnets still hide deeper mysteries. One of the strangest involves the nature of magnetic poles. When you examine a magnet, you find two poles, north and south. If you break the magnet in half, you might expect to isolate the North Pole from the South Pole, but that never happens. Instead, each piece becomes a smaller magnet with its own north and south poles. No matter how many times you cut the magnet, the two poles always appear together. They cannot be separated. This behavior is very different from electric charge. Positive and negative electric charges can exist independently. You can isolate a single electron carrying negative charge or a proton carrying positive charge. But in magnetism, isolated magnetic poles, called magnetic monopoles, have never been observed. In Maxwell's equations, this idea appears in a very simple statement. Magnetic field lines always form closed loops. They do not begin or end at a single point the way electric field lines do. Instead, they leave the North Pole of a magnet, curve through space, and return to the South Pole. For more than a century, physicists have wondered whether magnetic monopoles might exist somewhere in the universe. Some theoretical models predict their existence, and certain grand unified theories even suggest that monopoles may have formed during the earliest moments after the Big Bang. Scientists have searched for them in cosmic radiation, in ancient minerals, and in high-energy particle experiments. So far, none have been found. The absence of monopoles remains one of the intriguing puzzles in physics. If a magnetic monopole were ever discovered, it would profoundly change our understanding of electromagnetic theory. Despite these unanswered questions, the practical power of magnetism is undeniable. Magnetic fields allow electric generators to produce power. They make electric motors possible. They guide compass needles, store digital data, and enable technologies like MRI scanners that can image the inside of the human body. In hospitals around the world, enormous superconducting magnets create fields strong enough to influence the tiny magnetic moments of atoms inside our tissues. By observing how those atoms respond, doctors can build detailed images of organs, and detect diseases that would otherwise remain hidden. All of these technologies arise from the same basic phenomenon. You feel when two magnets push against each other in your hands. Yet even after exploring atoms, electrons, relativity, and electromagnetic waves, we still arrive at a surprising conclusion. At its deepest level, physics cannot always answer every why question in the way we might hope. Sometimes the most honest answer is simply that the universe follows certain fundamental rules. Electrons repel each other because that is one of the basic laws built into the structure of nature. And when we feel the invisible push between two magnets, we are experiencing those laws directly. When we reach this point, many people still feel that something is missing. We have talked about electrons, magnetic domains, fields, electricity, and relativity. We have seen how moving electric charges create magnetic effects, and how Maxwell's equations connect electricity, magnetism, and light into one unified description. But even after hearing all that, a curious mind will still ask the same question again. Yes, but what is magnetism really? That question is more subtle than it appears. In science, especially in physics, we eventually reach a level where explanations stop being mechanical pictures and start becoming descriptions of rules. At that level, the best we can do is describe how nature behaves with extreme accuracy. The deeper reason behind those rules may simply be part of the structure of the universe itself. This idea can feel unsatisfying at first, but it actually reveals something remarkable about how science works. Science does not begin with final answers. Instead, it builds layers of understanding step by step. Each layer explains a set of observations using deeper principles. For example, if someone asks why objects fall to the ground, we might say it is because of gravity. If they ask why gravity exists, we explain that mass curves spacetime according to Einstein's theory of general relativity. If they continue asking why mass curves spacetime, eventually we reach a point where we must admit that this is simply one of the fundamental laws we observe in nature. Magnetism belongs to that same category of fundamental behavior. However, the story becomes even more interesting when we explore the extreme conditions where magnetic effects reveal new and surprising phenomena. One of the most dramatic examples occurs when materials are cooled to extremely low temperatures. Under ordinary conditions, electric current flowing through a wire gradually loses energy because of resistance. As electrons move through the metal, they collide with atoms and other electrons. These collisions convert some of the electrical energy into heat. That is why electrical devices warm up when they operate. But when certain materials are cooled close to absolute zero, something extraordinary happens. Their electrical resistance disappears completely. The material becomes what physicists call a superconductor. In a superconducting wire, electrons can flow without any loss of energy. If you start a current circulating in a closed loop of superconducting wire, that current can continue flowing for years without slowing down. There is no friction at the microscopic level to stop it. This phenomenon is not just a curiosity of laboratory physics. It reveals something profound about how quantum mechanics governs the behavior of electrons in matter. When a material becomes superconducting, enormous numbers of electrons begin to act together as a single coordinated quantum system. Magnetism interacts with superconductors in a very unusual way. Normally, magnetic fields pass through most materials easily, but a superconductor actively pushes magnetic fields out of its interior. This effect is known as the Meissner effect. Because the superconductor expels the magnetic field, something spectacular can occur. If you place a small magnet above a cooled superconductor, the magnetic forces can balance the weight of the magnet. The magnet begins to float above the surface. This is not a trick or an illusion. It is a direct consequence of the interaction between magnetic fields and the quantum behavior of electrons in the superconducting material. The magnetic field lines are forced to bend and rearrange themselves in a way that creates a stable, levitating position for the magnet. If imperfections exist in the superconductor, tiny channels of magnetic field can become trapped inside the material. These trapped regions lock the magnet into position, allowing it to hover, even if the superconductor is tilted or moved. Physicists call this phenomenon flux pinning. A magnet frozen in midair reveals that magnetism is more than just a force. It's a manifestation of deep quantum interactions. These interactions play a crucial role on a planetary scale. Earth behaves like a giant magnet with a molten iron core generating electric currents. This magnetic field forms a protective shield, deflecting solar wind that could otherwise strip away our atmosphere and expose us to radiation. It even guides particles toward the poles, creating the glowing curtains of color we call the auroras. It is essential for the survival of life. But magnets hold a deep mystery. While electric charges can exist alone, magnets always come in pairs. Every magnet has a north and a south pole. If you cut a magnet in half, you get two smaller magnets. No matter how small the piece, the poles always remain together, forming closed loops through space. Physicists call a hypothetical single magnetic pole a magnetic monopole, but none have ever been found. For decades, scientists have searched for them in cosmic rays, particle accelerators, and ancient minerals. Some theories suggest they might have formed during the earliest moments of the universe, shortly after the Big Bang. If even one magnetic monopole were discovered, it would transform our understanding of physics. Despite that mystery, magnetism remains one of the most powerful and useful phenomena in nature. It connects electricity, light, atomic structure, and even the protection of our planet through Earth's magnetic field. All of these effects arise from the same fundamental interaction between electric charges and the structure of space-time. So when you hold two magnets and feel that invisible push between them, you are not just playing with a simple object. You are experiencing one of the basic laws of the universe directly through your fingertips. And perhaps the most remarkable part of all is that the human mind, evolved simply to survive in a complex world, has managed to uncover the principles behind that invisible force. The more deeply we study nature, the more we discover that even the simplest everyday experiences are connected to profound truths about the universe. Magnets are a perfect reminder of that. Something that seems ordinary at first glance turns out to be a window into the hidden structure of reality itself.